We have Fabian Yamaguchi, vulnerability extrapolation.
Almost.
I know.
Okay. Hello, my name is Fabian, and I work for Recurity Labs in Germany. The title of the talk is Vulnerability Extrapolation. And you've probably never heard the term, which is because I made it up. But I think that this is actually a practice that you've probably carried out yourself many, many times. And that all that's really missing is some kind of method or tool to help us carry out this strategy effectively. So the basic idea of vulnerability extrapolation is to understand that many bugs don't just exist alone, but they follow certain patterns. And as you audit more and more code, you see that there are often bugs that are just like the bug that you've just seen. So wouldn't it be nice to have some way of seeing whether if you already have one vulnerability, you can find other vulnerabilities just like that in the code base. And that's the basic idea. Now, that will mean that the vulnerability follows some sort of pattern. So the question arose whether maybe we can use algorithms from fields which deal with pattern recognition, like machine learning, to achieve this, and to exploit the patterns in this data, to get more ODE out of the ODE that you already have, or out of the bug that has just been disclosed. And this is what this talk is about. We build a method to do this, and I'm going to show you the method. And since it's BlackHat, which is very practical conference, I'm going to show you how this can be used in practice. And we're going to have a showcase. I'm going to show an ODE in FFmpeg, which is a multimedia library used with mPlayer and VLC. And basically how we found this ODE using this method. All right. But first, a few words about code auditing in general. I always think it's a lot like getting into some new area of mathematics, where basically you see that, well, it's mathematics, it's all the same, basically. But then you discover that there's vocabulary here. There are certain, people express things in certain ways, and there are patterns in argumentation. And just like that in a code base, you see that certain ways of expressing yourself in the code base and certain programming patterns you see over and over again. And once you start to understand these patterns specific to the code base, it becomes a lot easier to reason about it. If you don't like that image, it's also a lot like Doom. You get dropped into this code base and you have no idea where you are, and all you have in the beginning is basically very shitty tools, a handgun of some kind, and you need to start figuring out what are the secrets of this wad. Where do I find which weapons and how do I use them against which monsters? And it's going to be different if it's a good wad, then it's going to be very different from your usual Doom experience, right? Okay. So you could say, stop being that romantic, right? We've found lots of bugs in the past simply by saying, grep memcopy and just checking those calls. And old security auditing tools like RATS and ITS4 and Flaw Finder, basically what they did was have a list of dangerous functions and say, oh, somebody's using, I don't know, sprintf, check that. Okay, so that's not very sophisticated, but it makes a point, which is, you often find stuff that's just follows a pattern which you have across code bases, and it's all not that difficult and wouldn't really justify what we're about to be doing. But think of fuzzers, right? Fuzzers is basically saying there's certain input, and we've seen this input blow up so many things. Of course, we're going to adapt it to the protocol that we fuzz, but basically, it's always the same. It's like, oh, there's a length field. -1 is, a good thing to choose here. right? So why? Because things tend to break in the same way over and over again. Or let's look at taint propagation, which is something rather academic. In this case, what people look at is certain API usage patterns, which are often connected with vulnerabilities. So for example, they have certain sources, like the function read, and certain sinks, like malloc, and then they basically trace what happens between these functions. In a way, this is very similar to what RATS and ITS4 did. It's just a lot more sophisticated because you're actually looking at the interaction of different API functions. But there is a problem about this. This is just all totally overfished. See, if you're going to look at the things that go wrong everywhere, then that's probably also the stuff that pretty much everybody has looked into. So that basically means it's no longer optional in a code base that people actually care about to just take this approach and say, well, it's all the same. You need to really study the specifics of the code base. Grepping for memcopy is not that much of a strategy anymore for code that people actually care about. So what we want to do is we want to find the secrets in this squad, right? The weak programming patterns that we have here and not just anywhere. And I guess that's also why, did my slide just, oh no. No, I thought there was a slide missing, but it isn't. And I guess that's also why manual auditing is still so successful, because people can actually look at what this program does as opposed to what all programs do wrong. So let's take a look at some examples to get to know to explain what I mean by API usage patterns. So this was a bug in Poplar. It's actually two bugs. So the first one is probably very easy to spot. Oh, by the way, Poplar is a PDF viewer. The first one is easy to spot. You have a calculation in the malloc, which is 4 times width times height, and width and height is specified by an attacker. So obviously you can overflow that. And further down, it's not on the slide anymore, you have two loops which go across, copy into this buffer and use width and height. The very, very basic stuff. Heap-based buffer overflow, basically. But there's the second bug. And you can't really see this bug unless you know this Cairo API that they use. So let's check this out. The Cairo API says the following. This function, and what they mean is the second function you see there, the function that creates the surface, Cairo image surface create for data. This function always returns a valid pointer, but it will return a pointer to a nil surface in the case of an error, such as out of memory or invalid stride value. In case of invalid stride value, the error says that the returned surface will be Cairo says invalid stride. You can use Cairo surface status to check for this. So obviously this hasn't been done. You can see that the surface is just going to be used in the next function, even though that's an invalid surface. Now, you can't really blame the developer that much because the idea of not returning, null, but some null surface, which kind of works but kind of doesn't, is just not that good an idea. And of course, that happens again. This is Events, another PDF viewer, and they have the exact same code. Again, the malloc. This time, the multiplication moved up one line, but it's basically the same. And again, Cairo image surface create for data. No check whether that actually worked. And then Cairo surface set user data. Okay. So this is the easy case because the API symbols matched completely. So you could just do this with grepping for a list of things and then something as easy as that. But does it have to be that easy? This second bug shows that that doesn't have to be the case. So this was a bug in libtiff. And what you see here is you have the buffer v and a call to tiff fetch byte array. And what this does is it copies data into this buffer. Now you're probably going to ask yourself, how much data? Well, the amount of data to be copied is in the dir structure, in tiff dir entry, okay, in dir. So you can't really see explicitly how much data will be copied, and the developer didn't see this either. So you have a stack-based buffer overflow. And you see the exact same, not exactly the same bug, but a very similar bug down below. Basically the same as says tif fetch short array instead of tif fetch byte array. And then in 2010, and this is interesting, you have the exact same bug, and this function didn't exist in 2006. So that kind of shows that the API is just dumb, you know? It motivates bugs. And of course, they did it wrong again. This time it says tif fetch data, but you know, it's all the same. Tif fetch data, tif fetch short array, they all follow some sort of pattern. Okay, so in this case, you could say tif fetch short array, tif fetch data, they are pretty much synonymous. And you want a method which can detect this as well. Okay, we had that, developers missed it, okay. So what I think this tells us is that, you know, while the times of grep memcopy may be over, there are still patterns of API use which motivate vulnerabilities, and yeah. And that's the idea of vulnerability extrapolation. You know, given a function, find a function similar to this function in terms of API usage patterns. Why? Well, because these are the functions which are most likely to contain a similar bug to the one you already know. Okay, so there's an information leak here, and that's pretty interesting to think of it this way. Each time somebody discloses a vulnerability, what they're actually doing is they're kind of giving you a sample of a bug as it exists in this code base. So if this follows a pattern, then actually maybe they are giving you ODE, which is the case for our example. Okay. So what do we have to do? Well, we've said similar a couple of times, but we haven't really said what we mean by that. And in the end, we want something, you know, to find functions sharing similar programming patterns. That, of course, means that first we have to extract programming patterns in some meaningful way. Okay, so how do we do that? Okay, so this is going to be a little different from usual security talks because we're actually going to look into other fields and see how they deal with similarity. I hope that you'll you know, enjoy rather than dislike this attempt. Okay, so let's see. Similarity is always a decomposition. It's a decomposition into the big picture and the details. So if you look at signal processing, in that case, you usually say that you know, the big picture is in the low frequent part of the signal, and the details is in the high frequent. So if you take the sine curve up there, the big picture is this is the sine curve. And you know, all of that gibber there, that's just the details, you know, noise. And if you were to try to map code directly to this, which I actually tried at some point, that wouldn't be very successful. So you kind of need to see this in a more abstract way and recognize that you can choose different ways of decomposing things into big picture and detail. So for example, if you look at the two rectangular things there, if rotation is a detail, then they're pretty similar. Okay, so you would say, you know, color is the big picture, shape's the big picture, and rotation is the detail. And then there's something very interesting that people do in face recognition, which is they say, well, you know, faces are not just some images, they're images of faces. So let's look at the most dominant patterns that you see in human faces, and then see how much each face corresponds to each of these patterns. And starting from a certain strength of the pattern, you just say, you know, this isn't that much of a pattern anymore. Let's just chuck this away. Okay, so we had that. So this is the same thing that we have to do for code. We have to decompose it into the big picture and the details. So while the big picture may be this interaction of TIFF API calls, TIFF fetch data, and TIFF set field, and so on, the detail may be something like, uint32 or int. It's basically all the same. Okay. You can think of this as zooming out on code, right? So if you zoom out on something, you start to not see the little details anymore. So if you zoom out in image processing, you just cut off at a certain frequency. When you do this in face recognition, you cut off at a certain dominance of the pattern. So if it's not that important anymore, we cut off. And that's the same that we're going to do with code. We're going to extract the most dominant API usage patterns in the code base, and then at some point just say, and these are not so dominant. We're not going to consider these. That's just noise. Okay. So the question remains, how do we extract these dominant patterns? How do we extract these images? And it's funny that we can actually use the exact same algorithm that people use in face recognition. And that is principal component analysis. And what you should know about machine learning algorithms in general is that they work on vectorial data, which means you somehow have to map whatever you're dealing with into a vector space, and then you can use machine learning algorithms. So for images, like the faces you just saw, there's a very natural mapping that you can apply. You could just say, take all the pixels and just put the brightness in the vector. Then each image is a data point in a high-dimensional space where the number of dimensions is equal to the number of pixels. Okay. So let's consider a small example. Let's say we only consider images with 2 pixels. That allows us to reason about this without not being able to draw it anymore. Okay, so if we only have 2 pixels, then we can put down each image as brightness of the first pixel and brightness of the second pixel. And the pixels in the upper right corner, the images in the upper right corner are images where both pixels have are almost white, something like that, have a bright color. And in the lower left, they're both black. And on the diagonal, you have the mixtures. So now you see a clear pattern, which is that either both pixels light up or they don't. That's the tendency. It's the clearest pattern. And that corresponds to, as you can see in the image, the direction where the data varies mostly. So think about this. This means that all we have to do to find dominant patterns in this space is to find the directions of highest variance, where the data varies most. Yeah. So you don't really have to deal with this problem anymore. You can give that to the math guys, and they've been working on finding directions of highest variance for years. And it turns out, all the software you need to do this is already there. These directions correspond to the eigenvectors of the covariance matrix. You can look all these things up in my paper, but it's really not that important, as long as you get the intuition of directions of highest variance. And to get these eigenvectors of the covariance matrix, you can do a truncated singular value decomposition, and you have very fast algorithms to do this for you, and you don't have to implement this yourself. So let's make use of this. Okay. So first thing we have to do is we have to map our code to a vector space, because otherwise we can't use principal component analysis. Okay. So the mapping I chose was the following. I started extracting all the functions in the code base and the API symbols they use. And then I represented each function by a vector where I'd note down whether the symbol was being used or not. It's that simple. Okay. Then you have a very high-dimensional space, but you see that it's sparse. You know, only a few entries will be 1, and all the others will be 0. Okay, so now we're in the vector space, and now we can use principal component analysis. Okay, so this is the only formula I'm going to show. I'm just saying this because, you know, you don't have to worry that I'll drift into too much mathematics here. But this formula is important because it shows how feature-rich the representation is which we generate by doing this. So we take the function vectors, and we align them in a matrix. And now we want to approximate this by representation of the functions and multiplied by the directions of the highest variance. And this contains the strength of these directions of highest variance, so the strength of the pattern. So this is the same formula, and this shows what we get from doing this decomposition. So this is to implement PCA, basically. Well, here in the columns, we get the most dominant patterns. So the directions in the space are the most dominant patterns. Here we have the strength of the pattern, and this is the representation of the functions in terms of these most dominant patterns. Okay. And also in the rows, we get a representation of the symbols in terms of these patterns. So suddenly we have symbols and functions in the same space. Okay, so here's a summary of the method, and then we're going to go into an example where you'll probably understand better you know, what this does. So we extract the functions, we extract the API symbols in the functions, we use that to map all the functions into a vector space. Then we do principal component analysis, and then in this new space, we measure distances to find out which functions are close to one another or which API symbols. Okay. Now we're going to go through an example, and I hope that when I'm done with the example, you will understand why, you know, going through all this trouble is worthwhile. Okay, so this example, in this example, we have 6 functions. These are the 6 functions. Yeah, okay. And there are always groups of 2. You have 2 GUI functions, and they contain overlapping symbols. Some symbols occur in both functions, some only occur in one. And you have 3 APIs, the GUI functions, the network functions, and the list functions. Okay. And all of these functions contain the symbol int. Okay. And now we're going to do the decomposition and show what this looks like, what the vector space looks like when we project onto the most dominant and the second most dominant API usage pattern in this toy example. And this is what it looks like. As you can see, int has been projected onto the origin, which makes sense because it's really not expressive. If you tell somebody, you know, the function contains int, then, you know, he doesn't know which function it is. They all contain int. And then you see the 3 directions, each direction corresponding to one API. And you also see that functions using the same API are close to one another or are at the same angle, and that the API symbols have been projected at the same angle into the same region. So what you get in this case is a lot more than just a method to extrapolate. You get a projection of your code into a vector space where functions sharing similar programming patterns are near to one another, as well as the API symbols which make up the pattern. They're also in that area. So here's a small example to illustrate why this makes sense. The symbol host end was contained in network function 2. All right, here. So when you measure the similarity between the symbol host end and network function 2, you get a pretty high similarity, 0.8. Now, network function 1 does not contain this symbol, but still, it uses the same API. So in a way, it should also be similar. And as you can see, similarity is still 0.34, and all the other functions, which are from other APIs, have negative values as a similarity score. All right. So I just said that. Okay. So don't get me wrong on this. you shouldn't start to browse in this space like graphically. While it looks pretty, you have a 200-dimensional space or something like that, and you can't really browse well in that. Okay. It turns out in this case that good old tables are a lot better, just tables where you see how similar something is to a symbol that you put into the machinery. Okay, so how much time do I have? Let's see, 42, okay. All right, so let's see this in action. Let's take FFmpeg and see what kind of questions we can ask our tool. Okay, so FFmpeg has a lot of different decoders for different file formats. And each of these has a so-called decoding context, which saves the state of the decoder. So now we would suspect if we were to use one of these decoding contexts, like flick decode context, for example, the method should tell us that there are a lot of other decoding contexts just like that, because obviously decoders use the same API, so these are, these are pretty much synonyms. And what you get is that the tool lists different kinds of decoding contexts. So you have 8 BPS context, A&M context, HIF context, and so on, all contexts. Okay. And here's another example. Since there's not much string processing going on in FFmpeg, we thought, maybe it makes sense to ask for where in this entire code base we can find string processing. So first of all, we took the symbol char, and we asked, what symbols are close to symbol char? And it said const char, string compare, snprintf, exit for some reason, string tall, fprintf. Okay, it makes sense, right? String len, it's the string API that it's extracted. And now comes a killer feature where you can say is, and now give me the functions which make use of this API, because they should be close by in that space as well, right? And you can look into this into more detail in the white paper. Oh no, it's not in the white paper. Let me think. In the diploma thesis, but you'll find that online as well. Anyway, these are all these are the functions using the string API, and that's very limited in FFmpeg. And you'll see that a lot of these are string and text protocols. So you have HTTP here, for example, SDP, RGSP, stuff like that. Okay. But I guess the most interesting application, and we're going to come to that now, is vulnerability extrapolation, taking that bug you have, getting a new bug for it. And let's try that for FFmpeg. Okay. So this was a nice story. I got this bug, I saw this bug on a mailing list in September 2010. And it's a bug in one of the decoders, which probably allows arbitrary code execution. And if we look at these decoders, then they all follow a very similar pattern. Basically, what they want to do is they want to write to this pixel array, and they will read information. They need to do this using an API of macros, which are all called AVRL or AVR something, 16, 32, 8, whatever. Depends on how much they want to read. Okay, so now what you see here, what went wrong is that this pointer, this index, yptr, can basically be set to any value in this loop. And it's going to be used to reference the pixel array. So what you get out of this is an arbitrary write to some address. And you also control line packets, so that all works nicely. Okay. So I asked the tool, what other similar functions are there? And the first thing it told me was that apart from flick decode frame 8 BPP, there's also flick decode frame 15, 16 BPP. And they had fixed the same bug in that function as well. And then I looked down at VMDD code, and it contained the same bug as well, but that one hadn't been fixed. Okay, so this is the bug in VMDD code. Again, you see this API of AVRL something to read the information that you need to write into the pixel buffer. And this time it's called frame Y. It's not called yptr, but basically you see them referencing the pixel array and then copying stuff into there and not checking whether the offset is okay or not. Okay. So I thought, it's BlackHat, and I shouldn't just give you that bug, but I should also show that it's actually a security issue. Because denial of service in a video player, nobody would care about that. It's not a security issue. But if you can show that it executes arbitrary code, well, then it's a security issue. So that's what we're going to do now. Okay. 47. Yeah. Okay, so if you haven't written an exploit recently, it's a binary exploit. It's really an adventure you want to go through. So this is just going to be a proof of concept exploit in a way, but a proof of concept exploit which executes your code. But the whole thing about the ASLR and DEP, they're there now. So it's gotten a lot more challenging in a way, and but it's real fun. So you should try it. Okay, so you probably can't read that. That's okay, because I just wanted to show that there are two aspects to this bug. The first one is the memory corruption aspect, and that's the one we've seen already. Yeah, we can write to places we want using this by setting frame Y and frame X. They're all ours. So we can specify the index, and we can write to some location. Okay, so if you look at this in terms of ASLR, that basically means since we're writing relative to a heap pointer, the whole segment moves along. So as long as we stay in the heap, ASLR does not yet get in our way. Now there's a bit of a constraint. If you look at the indexes, those were 16-bit. And when you do the math, you see that you can write to any place except for this offset. And that kind of sucks, because it turns out that what we want to overwrite is in this interval. Okay. So first thing I wanted to do was get past this limitation. But first, let's consider, what do we want to overwrite? Does this limitation even affect us? And it turns out that shortly after the vulnerable function vmddcode is called, we get a call to avctx release buffer, and this is a function pointer. And if we can overwrite this function pointer, then obviously we can redirect the flow of execution. Now this structure, avctx, the AV codec context structure, is allocated as the program is started. So it's usually further up, and it's in that interval that we can't write to, and that sucks. So we have to find some way of getting past that limitation to overwrite the release buffer pointer. Okay, so second aspect. So this was fun. Actually, the decoder doesn't just take frames independently, but it has a state. Okay, so if you can modify the state, maybe you can get past the limitation. So the state is saved in this variable s here, and as you can see, there's a way of saving an x offset, which is equal to the frame x that you specify in one of the frames, in sx off. Okay, and this will then be subtracted from all the frame x's which come in later frames. Okay, so if you first go into this block and save something in sx off, and then you manage to skip this block, the next time sx off will be subtracted from frame x. So now if frame x is 0, it wraps, and you have minus 30 or whatever. So you exploit this with 2 frames. Okay, so the first frame is used to set the offset, and the second frame, we do the override. In the first frame, you don't even trigger the memory corruption bug yet. All you do is you save your offset in sx off, and then you supply a frame where frame x is 0, and you skip that block, and then frame x will be set to minus sx off, and then you're in that interval where you want to write to. There you go, second frame. Yeah. All right. So now we can overwrite at higher positions in the heap, and so now the only question that remains is where do we want to jump, and where do we go from there? And there's ASLR, but if you don't compile your code position independent, the main executable, then it can still be the case that you'll find something useful at a constant address. And that was the case for mPlayer, at least for Ubuntu and all the distros I tested. And what you find is a call to system and move whatever is at a EHX onto the stack. So basically, whatever is in EHX will point to a string that will be executed. Will be interpreted as a shell command and executed. So luckily, EHX points to the AVCTX structure. So what I started spraying was AVCTX structures, which would contain this address in the release buffer, and shell code, shell commands, which are kind of the shell code here, in the beginning of the AVCTX structure. So then, so then we'd be done, and I'm giving a demo. So if you didn't understand something that I just said, you may in the demo. There we go, demo. Demo. Okay, so I'm a coward, so I made a video. I'm sorry about that, but I was kind of nervous about this presentation. So anyway, let's go through this. Ah, damn it, I only have the image on this screen. Okay, so first of all, we start mPlayer in a debugger. Okay. And now we run a first exploit, and all this will do is prove that we can overwrite the release buffer pointer and have it point to 41, 41, 41, 41. Okay, so, and here's a nice thing. You can call this thing MP3, and mPlayer will still detect that it's actually not an MP3. So that makes it, more realistic, because, if somebody gives you a VMD file, then you probably don't even know that you should put it into mPlayer. Ta-da! 41, 41, 41. Okay. And then we look at the stack trace, and we see, yes, we're in that function, VMD video decode frame, and look at the release buffer pointer, and see that it is 41, 41, and so on. So now, we look at the code where we want to jump to. Okay, so search for system, and we see the second match, and this is the address that we're going to jump to. Okay, and now we run the actual exploit, which does the spraying. Exploit, and boom. ls echo pwned kill all mPlayer, but it was already dead. Okay. Okay. So now that we've shown that this can be done in one case, you kind of want to know how do we evaluate this kind of method? How do we show that it's worthy in general? Well, here are a couple of things to consider. If the code base simply does not contain another bug like this, then you're not going to find it. So going the route of saying, let's just take lots of projects and show that it can extrapolate. Yeah, you can do that, but it's not gonna give you data you can depend on. Second, all we see is basically things following the same API usage pattern. So what we can't do is if somebody were to implement the exact same functionality, but with different means, then we wouldn't be able to detect that. So it also doesn't make sense, to ask whether we can find, construct code with similar semantics where this doesn't work, because obviously it will not work. Okay. And third, even if they use the same pattern, it doesn't have to be used wrong. So you can't just do something like bug counting. What we can show is the ability of the tool to discover functions using similar API patterns. And we can do that by going ahead and actually manually extracting functions from different code bases which use the same kinds of patterns, and then looking whether the tool could have detected this as well. And this took quite a lot of time to extract this stuff manually to do a good evaluation, but yeah, it was worth it, you'll see. So what I did was I extracted code from the Linux kernel and from FFmpeg, and I had different groups: decoders, network functions, keyboard probe functions, sound-related functions, and demuxers. And what you see in the image here, in both of these images, is each of the pixels represents a similarity between two functions. And they have been aligned in such a way that all the decoding functions are up here, all the network functions here. So now you can compare how well it managed to differentiate these groups. So what you want is that decoders are all very similar. So this should be black, 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 black. Network functions should all be similar, and so on. And the groups should not be similar to all other groups. So this should all be white. Now this is what you get when you do this in the original space, right? Where all you've done is basically note down which API symbols are used by the functions. And you see that, yeah, well, you can kind of see that there's a group, but there's also a lot of white spots in here which don't make much sense. And then you do PCA, and suddenly the signal becomes a lot stronger. So you have more black on the diagonal, in contrast to that white on everywhere else. So that kind of highlights how PCA can be used to denoise this, to extract that big picture I'd been talking about before. Okay. So, in summary, what I think this shows is, well, there are lots of patterns in your bugs. This doesn't show that. That's the assumption, basically. But it does show that there's this info leak. When somebody discloses a bug, they're giving you a template of what's going wrong. And that's especially nice for you if you're just getting into a code base, because usually then you know nothing about it. And having a set of bugs that existed in the past gives you a lot of information of what can go wrong here. Okay. Now, that also means that if you fix a bug and you don't do any extrapolation, as is the case with FFmpeg all the time, this kind of bug was actually disclosed, I think, 2 days ago. And before that, a month ago. So this pattern is very strong in FFmpeg, and you'll see these kinds of bugs pop up in the future, I'm very sure. Okay. Yeah, you may be disclosing related ODE. That's the point. So where do we go from here? Well, for this method in particular, let's stay here for now. This will probably work very well on binary. And in that case, it makes even more sense, because binary is just huge bunch of data, and you really need methods to help you navigate here. And to be able to find functions using similar API usage patterns makes a lot of sense here. Secondly, you might, if you're into machine learning, you might ask yourself, why did you use PCA? Is there any justification for that? And basically, justification is PCA is the vanilla algorithm, and I want to show in general that it makes sense to use these machine learning algorithms in this context. But some tests I've been doing basically reveal, although that data is not very good yet, that NMF is probably a lot better, and that makes sense. And we can talk about this later if you're into this, but I'm not going to explain it at this point. And what we're currently investigating, especially in because of the fact that we want to apply this on binaries, is whether we can also take structural features in account. Find functions with similar structure and API use. Because obviously, when we do this on binary, we're missing a lot of API symbols because all we have is the function calls. So we need some more information. So maybe we can use the structure. Yeah, a friend of mine is currently working on that for his thesis. Okay. But there's a more general aspect to this work. And I think it's that it may make sense to use these kind of algorithms for machine learning. There's a lot of potential in security to use machine learning in security that way, yeah. Because there are so many patterns. And these are just some ideas. So for example, you could learn context-free grammars from input to generate fuzzers. Or you could cluster fuzz traces to group input that hits the same bug. Often people come up to you and say, I have 5 bugs in this and that, but really it turns out to be just the same bug, just hit in very similar but slightly different ways. You could try to build a more robust OS and rate limit detection for port scanning. And this is a very new idea I'm looking at right now, which is heap chunk usage patterns to identify how APIs interact at runtime. But you see the question mark there, so that's not something that I can say much about right now. Okay, so final words. Whenever you encounter patterns in security research, or you need to make some fuzzy decision, it may make sense to give machine learning a shot. That's the overall message I want to give, apart from all the, showing how something got exploited and using some particular method. That's the overall thing I want to say. And also, looking into other fields and what they're doing is not just, it may be worth your time. It's not just to relax or to see something else for a change. It may be that at some point these things converge and that you can actually make use of techniques from other fields. All right. Thank you.